Hello and welcome back. In this section, we will look at a simple example of the application of the Boltzmann equation that relates the absolute entropy to the number of microstates of microscopic arrangements that are consistent with a specified macro level specification of the state of a thermodynamic system. Okay. So, an elementary application of S equals Boltzmann's constant multiplying the logarithm of omega. Let's think of 1 mole of our favorite vehicle in terms of which to illustrate and develop our understanding of thermodynamics, 1 mole of an ideal gas. And let's say this gas is confined to a volume, let's call it V, and draw a picture. So that's the volume V, and we have Avogadro number of particles. So 1 mole n Avogadro particles, atoms or molecules, confined in this volume. Okay. How do we count the number of possible arrangements of the molecules in this box? One way to do that is to divide this volume into cells, into little boxes, like so. And let's say each of these little boxes has the volume, I'll call that V0, V subscript 0 equals volume of each cell or box. Okay. And now what we do is we count the number of ways we can put Avogadro number of particles into all of these cells that we have. So let's see. The number of such cells equals the total volume divided by the volume of any of the individual cells, right? Each cell has the same volume, they each have volume V0, and what we will see is we are introducing these cells, we are introducing these little boxes here as a calculational tool, as a device that enables us to calculate this number omega. But once we have completed our calculation, the cell volume drops out and it is no longer relevant. It's a tool that enables us to estimate what this number omega is, but otherwise is not going to play a major or an important role. Okay, so that's the number of cells. We have n Avogadro particles. How many arrangements? So let's see. The first particle can go into any one of these cells. So that can go in V divided by V0 ways, because that can go into any of these cells. The second particle also can be placed in any of these cells. Why so? Because remember, we are talking about an ideal gas. So let's say we place the first particle in here. The second particle can go anywhere. It could go here, could go here, it could also even go here. Why so? Because for an ideal gas, the assumption is the particles are point particles, and we can put howsoever many of them we want into any of these boxes. Could go here, any one of these. So all of the cells, including the first one, the one the first particle went into, are still available to the second particle, because we've made the assumption it's an ideal gas for which the particles have 0 size. How about the third particle? Same story. Also V divided by V0 possibilities. So the first 3 particles, let's call that omega sub 3 for 3 particles. they can go in how many ways? V divided by V0, multiplying this to the power 3. So many, multiplying so many, multiplying so many ways. Not quite done yet. We have to divide by 3 factorial because the particles are all identical and indistinguishable, and we can switch them, we can swap them around among each other without noticing the difference. Counts for permutations. Of 3 identical particles, because we cannot tell them apart, they are identical. So whether it's particle 1, 2, 3, 3, 1, 2, 3, 2, 1, 2, 3, 1, 2, 1, 3, we cannot tell the difference. All of those look the same. Okay, what if we have an Avogadro number of particles? Omega then becomes 1 divided by the factorial of Avogadro's number, multiplying the V divided by V0 to the power of Avogadro's number. So the entropy, Boltzmann's constant multiplying the natural logarithm of omega, becomes Boltzmann's constant multiplying the natural logarithm of 1 over the factorial of Avogadro's number, V divided by V0, that's raised to the power of Avogadro's number. Or S becomes minus kb natural logarithm of the factorial of Avogadro's number plus kb multiplying n Avogadro multiplying the natural logarithm of V over V0. Okay, how did that happen? I got to there by the following steps. That becomes kb multiplying the logarithm of 1 over n Avogadro factorial plus the logarithm of V over V0 to the power n Avogadro. The logarithm of x multiplying y is the logarithm of x plus the logarithm of y, and that is minus kb logarithm n Avogadro, this term, plus the logarithm of this quantity V over V0 to this power is simply n Avogadro, the power comes down, multiplying the logarithm of this quantity, n Avogadro kb logarithm of V over V naught, right? So that's the entropy. Carry that over to the next page. So the entropy, due to the configurations, due to the number of ways, the disorder associated with the number of ways we can arrange the atoms, becomes factorial plus the gas constant R multiplying the logarithm of V over V0. Remember, kb multiplying Avogadro's number, that is simply the gas constant R, as kb multiplying n Avogadro equals the gas constant capital R. Okay. This is the entropy, or a measure of the disorder that is associated with the number of configurations or arrangements in which the molecules can be placed. How about if the volume goes, say the volume starts at V1 and the temperature starts at temperature T, and we go to a volume V2 and keep the temperature the same T. Let's ask what delta S is for this change of state. So this 1 mole of our ideal gas starts at a volume V1, goes to a volume V2, and the temperature stays the same. We will see why it's important to keep the temperature the same in a moment. Working with this expression for the entropy, we have delta S is going to be S, the volume is V2, minus S when the volume is V1, same temperature T, the temperature is not changing, T is fixed here. That gives us R logarithm of V2, that's a 2 over V0, minus Kb logarithm, the Avogadro's number, factorial of that, minus entropy when the volume is 1, R logarithm of V1 over V0, minus Kb logarithm of n Avogadro factorial, minus Kb logarithm n Avogadro factorial, minus of minus. Lo and behold, these cancel out, and we get R logarithm V2 over V0 minus R logarithm of V1 over V0, which is R logarithm V final over V initial. That's delta S. Now, you may remember that some time back, using the delta S integral from 1 to 2 dq reversible over T, combining this with the first law and equation of state PV equals nRT, we obtained delta S was n multiplying R logarithm of V2 over V1 for isothermal change in volume for n, put that in quotes, moles of an ideal gas, right? We obtained this in our discussion of calculations of delta S. But what do we have here? For 1 mole of an ideal gas, we have obtained R multiplying logarithm of V final over V initial. This is simply what we have here, what we already obtained, where n was equal to 1 because we are working with 1 mole. Okay. So we have obtained our thermodynamic result that we obtained earlier using macroscopic thermodynamic arguments by using a counting and number of arrangements type argument. Okay. Remember, I mentioned it's important we are keeping the temperature fixed. Why is that? And that's because this is simply the entropy associated with configurations, with the number of arrangements of atoms or molecules. More generally, and I don't want to get too deeply into this, but we could say the entropy or the disorder has contributions from number of configurations, that's the number of arrangements of atoms or molecules, plus entropy associated with molecular vibrations, plus entropy associated with molecular translation, translational motion, molecules flying around, etc., etc. If the temperature is fixed, then the disorder or the molecular motion associated with vibrations, S associated with molecules flying around, center of mass motion, molecular translational motion, remain the same. For example, the Maxwell-Boltzmann speed distribution, remember that? We spoke about that a long time ago when we started out. Maxwell-Boltzmann speed distribution or velocity distribution is unchanged. So if we keep the temperature fixed, the distribution over molecular speeds and velocities has not changed. The intensity and extent of molecular vibrations does not change if we keep the temperature fixed. So these contributions to disorder, the vibrational contribution to molecular disorder the disorder associated with translational motion, these all remain the same. So these, the vibrations, translations, molecular rotation for that matter, those do not contribute to delta S. All that contributes to delta S under this situation, fixed temperature in this situation, is the configurational entropy. So the volume is going up, which means the number of places the atoms and molecules can inhabit, the number of relative arrangements of their centers of mass, that changes as the volume goes up. If we keep the temperature fixed, all of these other contributions to disorder remain the same. So delta S, when we subtract going from one volume to another, which is what we did here, the translational, vibrational contributions are the same at the same temperature. So those cancel out, and this is all we have, and that brings us to what we had before. Now, that raises the question, can we find a way to build in the translational, vibrational, the motional contributions to the entropy? Can we add those in to our absolute entropy by using S equals k Boltzmann logarithm of omega? Yes, we actually can do that. That is a well-developed subject. It's a well-understood thing how we actually count in such cases where we are talking about distributions over speeds, distributions over vibrational states. But that takes us too far into the field of what is called statistical physics, and this may be as far as we should go. That said, I want to return to another curiosity that comes out of the third law of thermodynamics. Remember we said, let's say, let me pick an example. Let me pick an example of iron. Iron, the symbol is Fe for iron, for ferrum, iron. And let's say at standard conditions, 1 atmosphere, temperature is 25 degrees C. Under these conditions, the standard state for iron is going to be solid. Iron is a solid at room temperature at 25 degrees C and 1 atmosphere pressure. So let's say we are interested in calculating the absolute value of the standard state molar entropy of iron. What would that be? This would be the integral from 0 Kelvin to 298 Kelvin of the heat capacity Cp per mole for iron in the solid phase as a function of temperature dt over T, because that's the integral from 0 to 298 Kelvin of dq reversible over T for the block of 1 mole of iron. There is no change of state. It starts out in the perfectly crystalline solid phase at 0 Kelvin, and lo and behold, at 25 degrees C, it's still in the solid state, so there is no change of phase or change of state. Okay, so that's the absolute molar entropy. Okay, so far so good. Notice the behavior of the integrand Cp per mole divided by temperature as T goes to 0. As T goes to 0, if Cp per mole remains constant, then Cp per mole divided by temperature behaves as 1 over temperature, and if you try to integrate 1 over temperature with respect to temperature, you end up with the natural logarithm, right? And the lower limit is 0, so you end up with natural logarithm of temperature, and you plug in the limit, you're taking the natural logarithm of 0, and natural logarithm of 0 is negative infinity, right? Because let's say the heat capacity is independent, rigorously independent of temperature. As the temperature goes to 0, Cp per mole over temperature is proportional to 1 over T. If you integrate 1 over T with on temperature, you get the natural logarithm of temperature. Plug in the lower limit of 0 Kelvin, logarithm of 0 is negative infinity, but we said that the entropy is 0 at 0 Kelvin, right? We said that the absolute value of the entropy is 0 as temperature goes to 0, not this minus infinity business. What's going on? Where is the problem? What's going on is something very, very interesting. The heat capacity as a function of temperature is proportional to temperature to the third power as temperature goes to 0 Kelvin, 0 K is 0 Kelvin universally. The constant of proportionality is different. So, for example, if you plot the heat capacity for any solid, for solids, I should say for crystals, plot the heat capacity in, say, joules per Kelvin per mole, plot the temperature here in Kelvin. For pretty much any crystalline solid you look at, the heat capacity will be roughly independent of temperature, and then it starts going down. It does something like this universally, and this behavior down here is Cp is proportional to the third power of temperature, where the constant of proportionality changes depending on whether you're looking at water, nitrogen, copper, iron, lead, what have you. The constant of proportionality is different, but this behavior is universal. And interestingly enough, this behavior, the fact that the heat capacity goes down to 0 at absolute 0, and it follows this T cube, this cubic power law, this was known experimentally many years before quantum mechanics was discovered. It turns out that this behavior for the heat capacity as a function of temperature, this cannot be understood based on classical mechanics. Understanding this curve or predicting this behavior for the heat capacity as a function of temperature requires the use of quantum mechanics. And in fact, experimentally, for explanation, experimentally this phenomenon, the fact that the heat capacity of solids went down approximately like T to the power 3 as the temperature approached 0 Kelvin, this was known many years, several years before quantum mechanics was discovered. It was a mystery because any Newtonian mechanics-based, classical mechanics-based picture of the heat capacity of a solid tells you it's going to be something like this. It does not give you this behavior. This is CM classical mechanical. To obtain this, you need quantum mechanics, the fact that the heat capacity vanishes. But the entire picture is consistent because if the heat capacity decays as T cubed, what does the entropy behave like? 0 Kelvin, I'll just put the lower limit here, call this T1 Cp dt over T. T1 is very close to absolute 0. Constant of proportionality, let's call that A for lack of a better word, A T cubed dt over T. It becomes T squared. So we get A and that correctly goes to 0 as T1 goes to 0. So it really is all internally consistent in the end. It all works out in the end because the heat capacity has this T cube behavior at low temperatures, which requires quantum mechanics to explain properly. And I should point out, because the history does matter, the correct quantum mechanical explanation for this behavior for the heat capacity of solids was discovered and elucidated by one Albert Einstein in one of his numerous major contributions to physics, with a major improvement, with a major filling out of important details in his work by Peter Debye a few years after that. Okay. So that said, this is as much as I want to say about our discussion of the third law of thermodynamics. Where we will go next is we have to look at some mathematical properties of the Gibbs free energy. Remember, the Gibbs free energy was enthalpy minus temperature times entropy, which is U plus PV minus Ts, and the Helmholtz free energy was U minus T times S. We have to look at some important mathematical properties of the Gibbs and Helmholtz free energies next. And the reason we need to look at some features of the mathematics of G and of A is that will be the bridge that takes us into applications where we can start finally using all that we have put together to tackle the physicochemical properties of elements, of compounds, to look at phase transitions, to look at mixtures. We will finally be ready to start tackling a set of different physicochemical transformations and their thermodynamic features once we have familiarized ourselves a little bit with a few mathematical properties of the Gibbs and the Helmholtz free energies. That's all for this section. Thank you very much again for your attention, and we'll look forward to seeing you next time. Thank you.